Hello, I'm Nikolai Privezhev, and this is a short overview of my current research projects and future directions. So more of this information can be found on my webpage, and here's a brief outline. Okay, so it can be roughly broken down into parts. One is part is more fluid types research, and more lately I have two projects related to mechanics of porous materials. Okay, so let's start with first one, this fluid transport and compatibility at structured and deformable interfaces. For many years, my research was focused on fluid flow in nanoscale dimensions in situations where slip boundary conditions are important. And more lately, my colleague and I got a grant from NSF on studying the diffusive motion of nanoparticles and its connection to slip boundary conditions. So this is important for experimental techniques like particle image velocimetry and in sensors in general. Okay. So now this is a simple interface and could be readily extended to other interesting situations. For example, if you have, let's say, self-assembled monolayer, or interested in the interfacial rheology of polymers and nanoparticles at the interface. And the other two cases is deformable interfaces and nanostructured interfaces. So these two situations are of particular importance because I recently got a Petroleum Research Fund award for the next 2 years studying contact angle hysteresis and transport of polymeric droplets on such interfaces. Good, so we then proceed, and then second project deals with microfiltration of oil and water emulsions using porous membranes. So this is an application-driven project which is relevant to oil spill remediation, water treatment, and water purification. So it started from the times when there's an oil spill in Mexican Gulf. So let's consider the following problem. So if we have water and dispersed oil phase, the question is then how to efficiently filter it out and push the water through the porous membrane, usually by applying a pressure across the membrane. Now, the problem here is under a relatively high pressure, these droplets will leak through and this membrane doesn't work. So one way out from this is to introduce a cross flow parallel to the surface of the membrane and induce maximum water flux. Okay? And that's what we've done with a student of mine in several papers. We considered various physical parameters and come up with a numerical phase diagram where, depending on the transmembrane pressure and cross-flow shear rate, we can observe a rejection of oil phase, then penetration of the oil droplets, and more subtle situation is when droplets would break up at the entrance of the pore and the membrane will be leaking. Okay, so more information can be found in the papers, and this research in general is relevant to experimental design and development of novel porous filters. Okay. Good. And then the third one on the fluid side deals with diffusion of either spherical or rod-shaped Janus nanoparticles, which are immersed in the Lennard-Jones solvents. In this situation, we have a nanoparticle that's constructed in such a way that the one part is non-weighting, it doesn't like liquid, and the other part is weighting, it likes liquid. So it turns out that diffusion of such a particle in a solvent is peculiar. Namely that under spontaneous motion of the center of mass, then non-weighting side of this particle will be oriented towards this displacement to reduce drag. And this type of motion can be picked up by special correlation function, which measures this average rotation angle towards displacement on a time scale, typical of the orientation of the nanoparticle. Okay. So this correlation function and many other features, we considered in a couple of recent papers. Okay. So this research is important in elucidating what happens if you have many of such particles and you're studying, say, self-ascent of those. Okay. Good. So we now switch gears and consider the topic that deals with structural transformations and mechanical properties of porous amorphous materials. So this research was done with a colleague of mine, Maxim Makeyev, and in the last couple of years we published 7 journal papers on this topic. So in general we consider a special system which is good glass former, and we quench this rapidly to lower temperature at constant volume, and in such a process there's a phase separation and solidification takes place, giving rise to porous structures like this. And depending on the average glass density, this structure might have a porous networks that are percolating, or on the other limiting side of large densities it would be a mostly solid phase with porous inclusion. So what we see here is some kind of intermediate case, okay, with medium range porosity. So when you deform material like this, one can go ahead and trace what is the pore size distribution and the average glass density. And our main conclusion that regardless of the deformation protocol, in this case is just simple tensile loading, then small pores, okay, in certain regions coalesce, okay, with each other, but in some other regions will form a dominant pore that will lead to ultimately to a failure of the material. It can be picked up by so-called scale density profiles, when you can see that there's a void is forming up. Okay. So this research is important for various structural applications and absorbent materials. Okay. More details can be found here. Okay. So lastly, I would mention the project that deals with actively deformed amorphous materials. You can keep in mind, let's say, metallic glasses that would have interesting mechanical properties, including high strength and low ductility, meaning that they are brittle. And nowadays, in general, there is interest in developing either mechanical or thermal processing routes, okay, to change the stored energy in these materials, and in this way tune either mechanical or physical properties of such material. So what we can see that here is one example where one can apply periodic shear deformation and see the structural relaxation of the material. So these results can be summarized in this plot where we have mechanical response versus strain amplitude, and what we see here that at low amplitude loading we have elastic regime followed by yielding, which is associated with the shear band, and there's atoms within the shear band will pick up diffusive motion. Okay. So what's interesting here is in the elastic regime one can view this sub-yield cycling as some sort of mechanical annealing, where over a consecutive cycling then the energy of the material is reduced, it becomes more dense and more brittle. Okay, so this is one example of how you can process material, and this details of this research can be found in the following paper. But overall, in the last 5 years, I wrote about 20 papers on this topic, which all can be found on my webpage. Good. So if you're interested in this, please contact me regarding any collaborations or possible graduate student research projects. Thank you.